Our next presentation is going to be tag teamed by two people, Lisa Schilling and Andre Soares. Lisa is a professor of medicine at Colorado, where she's board certified in internal medicine and clinical informatics. And what she's going to talk about, and she participates in the evidence-based evidence-based medicine on FHIR work group. Andre is also in Colorado in information sciences. And I think he's going to be the second presenter. Lisa?
Hi, everyone. I'm very grateful to be invited to this presentation, this symposium, and I'm a fan of so many of the people who have presented both last week and this week, so this is really phenomenal. Andre and I are tag teaming this presentation, and it's titled Computable Evidence, Evidence-Based Medicine, the EBM on FHIR project, and we're going to switch off kind of mid-presentation, so don't leave when we do that. So first, I just want to make some acknowledgements. So this work is really the work of many collaborators and members of the HL7 FHIR, EBM on FHIR work group, and the COVID-19 Knowledge Accelerator, or COCA projects. And there's really too many people to name, but these projects are led by Dr. Brian Elper, who is one of our discussants today. So, and we also want to thank Brian because we borrowed some slides from him. So some of the things that we're going to cover today are, we want to make sure that people understand kind of the purpose and value of computable evidence. And I think based on some of the prior presentations, this is actually obvious to people. We want them to become familiar with the EBM on FHIR Working Group project. And we want them to understand kind of the applications of this work and how these applications can serve the Cochrane community's goals for evidence synthesis. There's a number of terms that are going to come up during my presentation today, and so just to outline them briefly, and I have a little more detail on them, but the Health Level 7 International, or HL7, this is a standards development organization for healthcare data. I'm going to also talk about the Fast Healthcare Interoperability Resources, or FHIR, so another standard for data exchange, our EBM on FHIR project, and then another topic that will come up is the COVID-19 Knowledge Accelerator project, if we have the time for that. So HL7 is an international standards development organization. They focus on healthcare data standards, and this is really to ensure kind of exchange, integration, sharing, retrieval of healthcare data. And you can think of these, many of these standards are actually applied to our electronic medical record systems, but also other healthcare kind of software and applications that are used. There's many members in HL7. It's a volunteer organization, and it has produced many products, including clinical document architecture that are used to exchange healthcare data, and then also the HL7 FHIR. So FHIR is a standard for healthcare data exchange that was really designed in 2012 to really kind of improve the efficiency of data exchange, to create kind of better, more usable methods, and really focus on high value data that needed to be exchanged between electronic health record vendors, but also other applications. And so there's an active community of developers for this standard, and it's also an application programming interface, or API. So this really helps support kind of the app economy. So not only do we want to make the data kind of standardized and readily usable, but we want to make it usable to end users who can build applications on that data. So our project, the HL7 FHIR, or EBM on FHIR project, is really to now take some of the best kind of processes and best practices from HL7 and actually extend these data specifications to what we call EBM knowledge assets. So remember, most of this, the HL7 standards and the FHIR standards, really apply to clinical and claims data. So really, data about persons and problems and populations, but not results of clinical trials. So that's where our take is to actually apply some of these best practices to what we call evidence-based medicine results or clinical study results. And the goal is really to make this knowledge fair. And I'll talk a little bit about the FHIR principles too. The EBM on FHIR project was started by Dr. Alper in 2018 and is a voluntary work group. And we have, I think, representatives now from over 8 countries and 10 different work groups. And the members are made up of computer scientists, informaticians, terminologists, software developers, software engineers. So it's a wealth of expertise. So many of you may be familiar with the FHIR scientific data principles, but these principles were published in 2016, and they're guiding principles for scientific data management in stewardship. What makes this so important is, these principles are really based on a lot of best practices that came out of work that had already been done in physics and in astronomy and other fields. And so the purpose here was really to define kind of standards for well-curated digital data objects. And I'm going to go through this in a little bit of detail because I want us to think about how this applies to the knowledge that we create with clinical study results. So we want data to be findable, right? And to be findable, it has to have a unique identifier, and that identifier has to be persistent. We also need to know something about the data. So we need, rich descriptive metadata so we know what that data is about. And then we need it to be indexed and registered in a way that we can search for it. We want data to be accessible, so we want it to be retrievable, and it's great if it's open and even better if it's free, right? We want it to be interoperable, so that means there has to be a formal shared language for knowledge representation of the data. And we want to use vocabularies and terminologies that allow us to kind of understand kind of the meaning of that data. And lastly, we do all this because we want it to be reusable. And to be reusable, again, we need rich descriptive metadata. We need data use agreements or other contracts or rules on how we could use the data. We need to know about the provenance of the data, and we need to kind of follow community standards. And those community standards are outlined in many of the kind of the components that I just mentioned. So now let's think about, whether we have this for the scientific knowledge that we have. Well, this is what we have now, right? If we talk about findability, I guess when we can search in PubMed and we can search in Embase, and I can find an article that hopefully deals with a topic that I'm interested in. It's accessible, I guess, for some. Maybe I subscribe to a journal and it gets delivered to my door, or I'm going through a website and downloading a PDF, or I have an HTML version. But that's, definitely limitations there, right? Is it interoperable? Well, it's not even interoperable as they're written and published right now, right? I, read and speak English, and if it was in Mandarin, it wouldn't work for me, and English may not work for other people, but it's especially not interoperable for computers. Is it reusable? I guess I can pass along my journal, and certainly people can reuse websites, but it's not really reusable by computers, right? Or information systems or other applications for the most part. Okay, so this is an example of just to kind of bring home and highlight a little bit what we're talking about when we say computable. So we may think back to, our parents, our grandparents, kind of calling up AAA, ordering the map for the trip and getting the outline of where they were going to take their drive. I guess, you could pass that on to a friend when you were done, but basically you needed that paper to get where you were going. And then, we saw things become digital, right? So now we have maps on a digital, we may have a CD, and I can pop that in my computer and I can see that map. But I can't do anything else with it. But it's not on paper, and maybe it's a little bit handier to carry around. Now, as we move to things that are executable, Now there's a software program that I can actually run on this program. Now I can compute distances on the data. Maybe I can create a map for my use and I can store that. So this is much more usable than kind of the print version of the information. But to be computable, now what I have and what we use today, right? We have a series of applications that we use them on our phone, we use them on the navigation system in our car. They're used in many other places. At this point, we're not even thinking about where the data is that actually drives all these applications. They just kind of work. We didn't have to pop a CD in our car. We didn't have to upload a database. Wherever that data is, it is working, it's feeding all of these different applications. So that's what we're looking for with the results of our clinical trials and research knowledge and systematic reviews. So what do we have now with clinical evidence? Well, we've got that print journal, maybe we've got an HTML format of it. There's certainly databases that we can execute on and we can search for things like using PubMed. So there's an example. And what we're hoping to do, and what the EBM on FHIR project is about, is really creating standards for the computable representation of knowledge. So Adam Dunn had already mentioned earlier in his talk how valuable this would be in the work that he's doing to start some of this. So what we have now, no, we don't have a standard for machine interpretable expression of clinical evidence. We don't have anything that's interoperable. And I'm not sure we have universal agreement about the right way to do that. We are beginning to work on that with the EBM on FHIR project. And we don't have a functional demonstration, although I think we are beginning with our work to actually have functional demonstrations, and we'll show you that. This group is already very aware of all the challenges and issues. I mean, we've got a 17-year gap right between scientific evidence and patient care. We have systematic reviews that may have half-lives of 5 to 6 years before there's new evidence that actually needs to be reviewed and potentially implemented and used in those reviews. And we've just got a wealth of clinical trials and systematic reviews every day. And so all of these things are kind of barriers to keeping kind of knowledge up to date. So we have too much knowledge that's buried in text, right? It's not readily usable for downstream applications and use. And we've heard a lot about some kind of technologies, tools, and ideas for actually beginning to address this. So this is what we do now. Our evidence source is often this human readable article. Humans may extract the information from those articles. And, we did see some novel methods for actually doing evidence extraction. But for the most part, it's a little bit one by one. Someone who's creating a biomedical knowledge database does it for their work. Someone who's creating clinical practice guidelines does it for their work. Another person who's running clinical decision support systems may do the same thing. And systematic review creators and authors may also be doing the same thing, but it's very one-on-one. And I have a quote from James Thomas here, and now I may have to pull another one from him on the massive catastrophe that are information sciences for knowledge, but the massive failure. But human effort is a scarce and valuable resource, and we do need to expend it only where automation is impossible, impractical, or undesirable. And I think we all, agree on this call that the creation of systematic reviews, creating them, maintaining them, and disseminating them all take massive efforts. And much of the work that we will kind of do in the future, the best ways will be kind of a semi-automation or this human-computer combination to do much of this work. So this is the pathway that we envision for the future, where this evidence source, so whether it's a randomized publication of a randomized controlled trial or a publication of a systematic review or some other source, that there's actually some evidence extraction that happens kind of right at the start. And that is probably, semi-automation or human and computer kind of both doing this work. And our example here is, that we're extracting kind of the PICO, the stats, the table one. So, the methods and the results from these studies. And that does result in a computable format. And this is where the EBM on FHIR project comes in. And that computable format can be used, multi-purpose. So whether it is to feed kind of a biomedical knowledge database that can be used by all these end users, so whether that's more specialized knowledge databases, whether it is clinical practice guidelines, clinical decision support tools and applications, or systematic reviews, but that they can all use those resources. And this would be much like if we think back to the example of all of the applications and tools and devices that work on GIS and geographic data, then this evidence use would be all of our tools and devices and systems that can actually work on the data that is our biomedical knowledge. And so what we think of here is that a publication, in a sense, shouldn't be just that human readable article, but should also be this computer readable article. So what if we published that instead of just one? And so, this does feed kind of this whole kind of healthcare knowledge ecosystem, right? Because we want to expedite this system and we want to improve it. So the evidence that we are generating through our clinical trials, through systematic reviews, actually feeds guidance. So these are our recommendations, decision aids that leads to action. And from action, we should be monitoring, observations, outcomes, completing studies, which then feeds back into evidence. So what we're hoping is to really expedite this healthcare knowledge ecosystem. And the next slide is going to be a transition slide. And I do want to just tie in to something that's been discussed previously on the panel. Dr. Soares and I have actually done quite a bit of preliminary work looking at the Clinicaltrialsgov database and actually exploring that as a source for EBM on FHIR and really aligning the EBM on FHIR format with clinicaltrials.gov. So identifying areas where there could be kind of almost a one-to-one mapping, areas where that is not possible, there just isn't the structured data in clinicaltrials.gov, or there isn't the use of standard vocabularies or terminologies. So those would need to be kind of included in that, or potentially even improved. The EBM on FHIR project is really working to, create a format that makes the knowledge of our clinical trials systematic reviews really meet those FHIR principles. So that knowledge is data and that we can use that in downstream use cases. But I'm going to turn the presentation over now to Dr. Soares, who is going to go into some of the details around what this EBM FHIR work looks like and what our products have been.
The goal here is to show some examples of the EBM on FHIR. Since 2008, like Lisa mentioned, EBM on FHIR has been extending FHIR in creating these FHIR resources. They start with evidence variable, and site group, and then also the data types for statistic and order distribution. And then last year with the COCA COVID Knowledge Accelerator group, 2 more resources were created, the evidence report and the citation. We're not going to discuss all of those. I'm just going to show examples of a few of those. So here we have the evidence resource. Here we have the list of data elements that include the evidence resource, includes metadata. It's used for evidence variables like PICO framework and statistic and the certainty of the evidence. And here we have, these different data types, have dates, strings, identifiers. So one of these examples is the variable row, which could be a population, subpopulation, exposure, reference exposure, measure variable, and confounder. These are codable concepts, and the EBM on FHIR group has created around 35 code systems to represent this type of data. So here's the variable row, and the next another example is the study type, which is also a codable concept, and that could be RCT, CCT, cohort, and so on. So I'm going to go through the process of showing the evidence resource and the examples how these are encoded in JSON code. So the evidence resource starts with the metadata. It includes IDs, identifier, title, status, data, copyright, authors, related artifacts. In this case, is pointing to a citation of the article that was used for this study. And one important thing to remember here is that the unique identifier makes this, in the terms of FHIR and FHIR, is findable. And the standard code system that we will talk about makes this interoperable. There are also several data elements that are for humans to read, so it can fit both human and computer readable content. And here, then, the evidence resource is used for creating and defining evidence variables. So here's one example of an evidence variable. It's classified with the code for subpopulation. So it's the P in PICO. It's for COVID-19 suspected, confirmed, and hospitalized requiring oxygen. And this example shows the reference to a group. So the subpopulation can be, the knowledge of that subpopulation can be embedded in the group resource. We're going to see that in more details later. And here's another example of a variable that was defined. In this case, is an exposure, is the I in PICO, is for dexamethasone. And then the observed variable is referring to an evidence variable. So it's a different type of resource for that specific case. The evidence resource also can record information about the synthesis type. In this case, is not applicable because this is a single study, but could be a meta-analysis. And also, it represents the study type of RCT, which is one of the codes I showed earlier for the study type. Then the two things that I mentioned before, the evidence resource is representing statistic and certainty. So for statistic, here's one example, the age-adjusted rate ratio of 1.595% confidence interval. So that information that is for humans to read can be broken down into specific data elements. So in this case, we have the rate ratio, which is also a code system. We have the quantity 1.15, and with the comparator equal, which is for computer systems to understand. We have the number of events, sample size, number of studies, and so on. It also we have information about the confidence interval. It's using a code system, and then we have the level 0.95 and the high and low range. So that information is recorded in a way that's for computers to use. And finally, in evidence resource, we have the certainty of the evidence. In this case, the certainty is showing that publication bias has no serious concern. And it's a long list of information, but there are some other examples with risk of bias. But that's how it is recorded in this structure. So the other resource I want to talk about is the group. From the beginning, we saw that subpopulation was pointing to a group resource. So we have this other resource that you can provide more information about the group. So here's the list of items for the group. Again, it starts with metadata and some specifics about the group, in this case, characteristics. But I would like to point out that a group can be used for person, animals, practitioners, device, medication. So it's not just for EBM, but we are using it's for the FHIR ecosystem. So here's one example of the group resource. So the group 16, that was the subpopulation, it's here. It's a type of person. It's for any age, COVID suspect, confirmed, hospitalized, requiring oxygen. And then this information can be codified using SNOMED. So we have the admission to hospital admission. We have the disease caused by severe SARS or suspected disease SARS. So that information can be codified and then available for computer systems to use. So what we do with this? The idea is that we can go from an article, codify that into IBM on FHIR and make that machine readable. And note here that the publication of the article was 3 days from when it was codified. So the information from the article could be already being used by computer systems. And then because we have the code, it can be sent, regenerate summaries for humans to read based on the information that's codified. And then after that, we can cite this report. And also here we have the example of a computable resource and you have the link to actually the code that could be used by other systems. So this is the overall idea of the IBM on FHIR. All the different resources, they can do similar things, and that's how we codify the knowledge of evidence into this structure. Because of time, we are happy to be invited for this presentation. Thank you for your attention. If you're interested in the IBM on FHIR and the COCO project, here's the tiny URL link that you can use. And me, Liz, and Brian are going to be available for a discussion.